Good evening, all. Today we are going to discuss about the principle and applications of spectroscopic technique in analytical chemistry. In today's particular lecture, we will cover this both absorptions and the emission spectroscopy in detail, and some minor details of the this MS. ICP-MS will cover it later on when we discuss the hypothetical techniques. But today we will see some of the intricacies involved while doing sample analysis in the mass spectrometry. So before going for these lectures, now let's have a recap what we have done so far. See, we had learned the analytical terminologies. So in the analytical terminology, we start with the very basic, what we call it samples. And the composition of the sample we discussed this is a mixture of basically analyte and a matrix. And analyte can be, there will be one single analyte or there will be many analytes are there. Or in case of synthetic sample, your matrix may be very simple one, but in case of environmental samples or the sample which is coming from the natures, you have a very complex matrix because we do not know the composition of the matrix. Then we have seen this importance of the calibrations, how to do the calibration functions, and then the sensitivity. Sensitivity, which is nothing but the slope of the calibration curve. Basically, whenever you are doing any calibration, there is a measurement of the x and y axis. So if a small change in x axis, what changes will come in the y axis? So that's will be qualified as a calibration. That will be calibrated. This will be quantified as in a slope of the calibration curve. And then we had discussed about the various analytical techniques. So there is basically three major analytical techniques are there. One is the absolute methods. The absolute method means nothing but it does not, the method which does not depend on the standard reference materials, or you can just do the chemistry and then get the quantification of that particular analyte. Okay, and then after doing one of the major advantages of this absolute method is that you are having a very small RSD values are there. That is the RSD value less than a 1%. It's really remarkable to get a RSD value less than a 1%, because in case of the other methods, the RSD value is generally in the range of about say 5%. Okay, so absolute methods, then these relative methods are there. So relative methods may all this whatever today we are going to discuss all the relative methods are there. Okay, relative methods means they need a calibration actually. So calibrations you have to plot in a calibration curve and then go for the analysis. So that's why we call it relative methods. So whatever the analysis are done, that is based on the relative to the standard samples. Then we come to the comparative methods. See, what is the difference between the relative method and the comparative method is that, see, in case of the relative method, it's not necessary that your matrix should be, matrix matching standards are there. So, but in case of a comparative method, so you must have a matrix matching standards are there. So then only you can do. In both the cases, you have to do a calibration curve. Okay. So in case of relative methods, it can be done by using a simple any standard samples. But in case of a comparative method, that should be a similar method. For example, if you want to do the analysis of a copper in any steel samples, so you must have a that steel only. So you whatever the calibration curve you will plot, so you will have a different concentration of a copper in some metal samples only. So that's the difference between the relative methods and the comparative methods. Then we had touched upon the solution and the stoichiometric. Solution, as we discussed, is nothing but a solute and a solvent. And then we how to write the stoichiometry of the equations. What is the how to see whatever the word appearing in the parenthesis. If it is G, it means a gas. If it is parenthesis say that S, then it means it's a solid. So basically, physical state of the matter can be put in the parenthesis. Whereas to balance the equation, we need a coefficient. So coefficients are there. By the help of those coefficients, you can balance the equations. Okay. Then we had seen the how the evaluation of the analytical chemistry. That analytical chemistry started from the gravimetry. So there are certain problems are there in the gravity analysis that if the precipitation is not complete, or maybe you are not getting a suitable precipitate, then those things have been overcome by using the volumetric. Actually, one more thing is there. See, gravity analysis is only possible when you are doing the analysis the percentage levels only. Then the ppm levels, say pp, or even in a less than a 1% samples, it's very difficult to do the gravity analysis. So then it comes to the genesis of the volumetric analysis. Volumetric analysis was nothing but is basically titration based. So the titration may be acid based titration, or redox titrations. And then comes the calorimetry. Calorimetry means the many of these analytes can be detected by just developing the color, and then by measuring the intensity of these colors, we can quantify the analytes in these things. And after discussing all those things, we come to the importance of sampling. The sampling, as far as the analytical chemistry is concerned, is basically is a very important steps, because once you had committed any errors while taking out the samples, then nothing will help you. Basically, you have, because you have not taken the proper samples. So whatever the best analyst you are, or whatever sophisticated equipment you are having in your laboratory, you are going to end up with the results which are not correct one. Then once you done the sampling, how to store the samples actually? See, during, because it's not always possible. You just take the sample and start doing the analysis. Okay, so there is a time lag is there. Is there any questions are there? कुछ तो पूछा किसी ने. नहीं, okay. Okay. Some popular comment. Okay. So because it is not always possible that you have to collect the sample and start doing the analysis. So during this process of the storage of the sample, or the process of transportation, you should not lose or contaminate your analyte actually. So lose means that if it is a volatile material, or that analyte may be absorbed on the vessels of the container, so that care has to be taken in that respect. And whereas there is certain additions also can be done. Suppose if you keep your sample, lead sample, you want to analyze the water samples, then there may be external contamination, atmospheric contamination of lead will come into the water samples. And then the sample digestion. Sample digestion again, this is a step which is again a very crucial one, because it is not always possible, whatever the state you had physical state you had collected your sample, to analyze the sample. Okay, in most of the cases, the sample resolution is required. Okay, so in that case, you should know how to bring out your analyte of interest into the solution from that matrix, and what kind of various combination of acids, or maybe what is dry etching or wet etching, or even fusion also is there. So what method has to be applied, so that you can get your analyte without losing any information about that analyte. Then we had gone through this intricacy with the environmental analytical chemistry. See, basically the environmental analytical chemistry and normal analytical chemistry is, normal analytical chemistry generally dealt with the synthetic samples only. Okay, the sample you synthesize into a laboratory, and so that you will be, you are in a position to give the analyst all the information about your matrix. Whereas in case of environmental samples, it is not possible, because you do not know the composition of the matrix actually. And then most of the time the environmental sample deal with a very low concentration, maybe in the range of a ppm and a ppb, and sometimes in the sub-ppb range also. Then we have discussed the various separation chemistry steps are there, that ion exchange, solvent extraction, and then comes to the chromatography. Because once you find out any analyte is there, how to use the various methodology to separate out the major matrix interference. So in this case, I have given you, for example, we want to analyze the iron and aluminum in the uranium sample. So how to remove the major matrix, that is uranium. So we have taken the help of a solvent extractions. In this case, we had removed by using the tributyl phosphate to remove all the uranium from the samples. Then in the section of the chromatography, we have seen how to various the chromatography can be distributed on the basis of mobile phase or the stationary phase, and then the mechanism of absorptions. What are the various steps by which the analyte interact with the stationary phase, and then depend on these various kind of this chromatographic system attached with the various kind of detectors. In this, we have seen up to the most sensitive in, I think, the fluorescence detector, where we have a detection limit in the sub-ppb range. So now let's come to the today lectures. See, okay. So today lectures we are covering first रेंज चल रहा है. अभी तुमने इसको लेजर पॉइंटर लगा दे तो माउस काम नेक्स्ट करने के लिए इसी करूँ नहीं हो रहा है वो भी डेफिनेशंस. ओके. Okay. So today's actually we are going to discuss about the spectroscopy, and then basically being an analytical chemistry, we are not going to detail the fundamental of the spectroscopy. So we are basically discussing the spectrometry and the spectrometric methods. What is spectroscopy? Spectroscopy is nothing but a branch of science in which the interaction of electromagnetic radiation with the matter is discussed. And whereas the spectrometry, the measurement of the intensity of the radiation with a photoelectric transducer or other type of electronic devices. So these all termed as a spectrometry. So that's today lectures we will cover up this flame atomic absorption spectroscopy, and then ICPOA, that is the electric coupled plasma optical emission spectroscopy, and some part we will touch about this ICP-MS. Just see the basics of this electromagnetic spectroscopy. So electromagnetic radiation spectrum basically is covered from the gamma rays to these radio waves. But when we are discussing in today's lecture, so we are going to concentrate only in this UV visible and the IR region. That is, visible regions about say 200 to 380 nanometers, whereas the visible region has been classified between 280 to 780 nanometers, and this infrared region about the 780 nanometer to 3000 nanometers. So it's a very small part of this electromagnetic radiation we are concentrating it today. So this what is the genesis of this spectroscopy? So basically the Bohr model, which say the quantized state actually. So what is the Bohr model? In the Bohr model of the atom, electrons travels in a defined circular orbit around the nucleus, and the orbit are labeled by integers, that is the quantum number n. An electron can jump from one orbit to the another by emitting or absorbing energy. So this, whatever the energy is getting absorbed or emitted, that's we measure it and termed as a spectrometry. And we are using these signatures of the atoms to identify and quantify the various elements. So generally the analyte in the lowest energy state, and then the stimulus causes whatever the way of you are exciting. For example, today what we are providing the heat energy to excite my atoms. Okay, so the stimulus causes some of the analyte species to undergo transitions to a higher energy state, to the excited state. And when this excited state de-excite by emission of electromagnetic radiations, and by measuring the energy and intensity of absorbed or emitted radiation, the spectroscopic information of the analyte will be derived. And this intensity is related to the analyte concentration, and that we use for the quantifications. And as a driving force for excitations of these atoms, or in say molecules, can be the heat, electrical energy, chemical energy, and particles beside the electromagnetic radiations are there. So you see, before moving further, I would like that all of you see, no science is developed. No science is developed in a one day. So this science, basically this spectroscopy, if you see this, first this is not but mouse, you remove this laser pointer. Okay, so this is how the various scientists we start from the 1700. That is Newton. That Newton used the word of spectrum to describe the rainbow of colors that combine to form a white light. And then there is so many other people that contributed from 1700. Then comes in 1913s the Bohr. Actually, in the Bohr, the first theoretical model that would give a quantized energy level that was in a quantitative agreement with the measurement of the hydrogen spectrum. But there are certain issues are still related because those calculations have not been done that accurate. And then comes, this Richard Singhal and his colleagues. Actually, they had developed the theory, and this theory known as quantum electrodynamics, and had its foundation and discovery of Dirichlet. This Heisenberg and this Paulis, it's a complete description of the interactions of radiations with matter and has been used to calculate the energy level of the hydrogen atom. You can see that. See the accuracy of better than one part in 10 to the power 11. So this is how the basis of this this quantification, whatever the interaction of the electromagnetic radiation with the metals, and then how we are using the signature which is coming from the various atoms, coming from the various signatures coming from the various atoms used for detections and as well as for the quantifications. And see, this is what we discussed up to now is like an atom. Similarly, in the case of the molecules, the excitation and de-excitation occur in the molecules after absorbing the energies, and these are the various, movements of electrons are there from this, basically from the bonding or 20 bonding, and because of these changes, that because of these changes, this intensity which is coming out of this changes is proportional to the atoms or molecules involved in this absorption and emissions spectrum, and these signals are basically quantifiable signals are there. Then this invisible spectroscopy, I think most of you, even if you are any kind of a BSc or even if you are a BSc physics, you may be having subsidiary in your first year. So invisible spectroscopy. Before going further, any queries up to our last two lectures? Friends, if you have any queries regarding the last two lectures, you can come forward and put your questions in the chat box. I do not know how many people are listening right now. So whatever the people you are, so if you have any queries are there, please come forward and ask me. Okay. So UV-visible spectroscopy basically dealing with the absorption of light in the range of 200 to 900 nanometers, and the transition that results in the absorptions of electromagnetic radiation in this region of the spectrums are transitions between the electronic energy level, that is from the one electronic level to the another electronic level, And generally, these transitions involve this the HUMO and LUMO. HUMO means the highest occupied molecular orbital and to the lowest unoccupied molecular orbitals are there. Generally, these are the most probable transitions in the case of a UV spectroscopy. And this is how, basically the ground state electronic levels are there, and then the excited state electronic states are there, and then whatever the various vibrations and rotational level which are associated with them. So these are the transitions coming from those things. So light in the invisible part of the spectrum is used to promote electrons from the ground state to the various excited state. And the particular frequency at which the light is absorbed are affected by the structures and environment of the chromophore, that is the light absorbing species. And when the excited electron can return, when this excited electron return to the ground state by vibrational transitions through smaller energy increment, and the absorbed energy appears ultimately heat in the solutions. And this is how we relate these changes by using the Beard-Lambert law. What is this Beard-Lambert law? Says that the intensity of the light decrease exponentially as it passes through a absorbing medium. Okay, and the absorption is defined by nothing but the intensity of the initial intensity by the intensity which is emitted, that is I0, I0 is the intensity of the incident light, and I is the intensity of the transmitted light which come out from the solutions. So basically, this is the relation in case of the Beard-Lambert law, that the absorption is equal to epsilon into concentration into the length of the whatever the medium you are using, because basically we are using here is a cuvettes are there, and basically in case of a multiple, if there is a multiple annulate are there, so absorbance is nothing but the additive properties are there. So in case of the multiple absorbance of a mixture is just basically sigma I0 to n, whatever the species of absorbing species are there, that is AI. So basically this becomes a it's the additive property. So it can be summation of all the annulating. And generally, as per the Beard-Lambert law, is proportional to the concentration, and the absorbance versus concentration generally just put in a straight line. But this is the case when we have an ideal solutions are there. Ideal solution means that it's meeting the conditions of the Beard-Lambert law, because the Beard-Lambert law is not followed in case of high concentration samples. And generally, whenever there is interaction between the solute and the solvent, then also it does not follow. So that's how we are getting it instead of straight line, getting a saturated, and we will get a plateau at the top of this thing. So generally, what is the reason for this? Because at a high concentration, the particles are becoming very close, and the average distance between the ions and the molecule diminished, and this will affect the charge distribution and extent of absorptions, and that is the reason why it causes deviations from the linear relation. And as I told you, that the chemical interaction sometimes the dissociation or reaction with the solvent also cause these deviations. बस ये स्कैन क्यों रहा है पहले तो नहीं होता था नहीं okay so these are the various kind of electronic transitions are there. See, in case of the organic molecules are there, the organic compounds are there, which involve the pi, sigma, and n electron. And in case of a saturated compound, saturated organic compound, the most of the transition are from sigma to sigma star, which comes less than 150 nanometers, and then n to sigma star, that is less than 250 nanometers. And then deep, that is a deep ultraviolet region. Whereas in case of a double bond unsaturated system, less energy is there. So most of the transitions are involving pi to pi stars, and then n to pi star transitions are there, which comes in the 200 to 700 regions are there. Then in case of a metal ligand complexes, there is charge transfer transitions are there. That is, the electrons move between the ligand and metals. And in this, one must act as a donor and other acceptors are there. Then in case of an inorganic, where most of the cases, if you are looking for an inorganic analyte and using the UV visible spectrum, then most of the transitions are the DD transitions are there. And additionally, transitions between the d orbitals that is split by the presence of the ligand, and these are generally a part of the all these transitions will be reflected in the visible region. This is generally a block diagram. A simplest UV visible spectrum is there, that is concerned a light source, and after this light source, there is a wavelength selectors are there that we call as the monochromators. And from this, a selective wavelength light will go to the samples, which is having a sample holders there, and then typically a cuvette, quartz cuvettes are there. Then we are having a light detectors. So most of the light detectors, they basically it can be, typically a photovoltaic tube or a photodiode arrays or the charge particle devices are there, because nowadays most of the detectors have been replaced by this CCD, and the light source can be a deuterium lamp or a tungsten lamps are there. So these are the wavelengths which is, in case of you're looking for any connection between the 160 to 375 nanometer, then we are using this deuterium lamp. Otherwise, we are having this tungsten lamps are there. So, and now there are certain, spectrophotometer xenon arc lamp, which is continuous from the 160 to 2000 nanometers, or more recently, light emitting diode LED also in the as a light source here. Then we discuss about this atomic spectroscopy, which is various this ICPOS or atomic absorption spectroscopy, or ICPOS, that is indirectly coupled plasma optical emission spectroscopy are there. So basically, atomic spectroscopy is the study of electromagnetic radiations absorbed and emitted by atom. And these are the signatures basically. Since unique element have a characteristic spectra, and atomic spectroscopy, specifically the electromagnetic spectrum or a mass spectrum, is applied for the determination of elemental composition. And it can be divided by atomization sources or by the type of spectroscopy used in the latter case. And the main division is between the optical and mass spectroscopy. The mass spectroscopy and generally the optical spectroscopy is that the mass spectroscopy expensive and is a complex, but the sensitivity is better than compared to the optical spectroscopy are there. Okay, once you want to sell out of this sensitivity part, then we have basically optical spectroscopy. They are often less expensive and easily available basically, because many people can afford those things. Hello, Rishabh, बहुत गर्मी हो रहा है, बहुत ज्यादा सफोकेशन हो रहा है, तो कितना एसी है? तो कम, क्योंकि बहुत मेरा पंखा चला देता है, हाँ, क्योंकि बहुत पसीना नहीं। अच्छा, हवा आवाज आएगा क्या? थोड़ा एक पे चला। Okay. So, because optical spectroscopy is often less expensive and performance adequate for many tasks, it's common. And atomic absorption spectrometer are one of the most, as I told you, they are the easily available slider there. And whenever we measure the energy absorbed, or we can measure the energy absorbed in case of atomic absorptions or the graphite atomic absorption spectroscopy, and whenever we will the emissions, then it can be done by using the ICP Korea, that is inductive covered plasma optical emission spectroscopy. Okay, so this is how the interactions of the radiation with the metals there. Basically, radiation interact with the inertial of electrons, and when the transition will take place, you will get a particular energy from the system, and this energy, when in case of a ground state to the excited states are there. So when we measure the energy absorbed, this calls a absorption spectroscopy because we can measure the energy which is absorbed there, and whenever we are measuring the energy which is emitted, it can be termed as a emission spectroscopy. And in the due course, in the next few PowerPoint, we will see that what is the distinction between these atomic absorptions and then the atomic emissions. See, one more thing let me tell you here. See, most of the analysis, see, almost about say 70% of the sample which is done, has been analyzed. So these are the technique actually made with both UV visible ICP OES or AES. That is AES with AV flame or a graphite foundation. More than 70% of the analysis has been carried out by using these two techniques. And generally, when we see this basically critical part of this portion, the ratio of the excited ground state atom is generally governed by these Boltzmann equations. With the help of the Boltzmann equations, explain the relationship, the population of the electrons and the ground state and the excited state. So one can evaluate this, the population, the ratio with N1 and N0. Okay. And whereas in this, in the ZEEMAN and G2, they are the statistics weight actually, where they're taken into account in the degeneracy of energy state and more than one state having the same energy levels. So this is how one can use the Boltzmann equations, which explain the relationship between the ground state and the excited state atom. And as I told you, this is the absorption spectroscopy. Whenever we measure the energy which is absorbed by the atom, termed as the absorption spectroscopy. And when we measure the energy which is emitted by the atoms, they termed as the emission spectroscopy. And because of these two different techniques are there, a lot of, I told you that more than 70 to 80% of the analysis has been covered by using these two techniques actually. See, I think this is the most crucial step. If you can understand this step, I think you can clear with most of your doubts. See, what we are talking now, we are talking only the atoms. And see, for example, in the samples, you are having aluminum chloride is there, you are having lead chloride is there, you are having lead nitrates are there. So how to bring those things into the atom actually? Okay, so this is the most crucial step. So whether your sample is a solid and liquid, so how you can generate the atoms or ions from this basically this physical state of your samples. So you can use the laser ablations. When you are using the laser ablations, directly you can put your molecule in the gas phase. Okay, in case of a solid sample, if you have solid sample and you use laser ablation, then you can directly use the laser energy and put your molecule in the gas phase. Okay, and once your molecule in the gas phase, what is that? You have to dissociate it. Okay, so dissociate that we have to get the atom in the gas in a gas phase. The next step is once your molecule in the gas phase, you have to generate the atom in the gas phase. Now, once your atom in the gas phase, then you have to further ionize it actually. You are giving the further energy, then you will generate ions in them actually. Okay. So these ions, for example, if I am carrying out the absorption spectroscopy, then these ions is not important for me. Basically, this become an issue for me, and how I want to avoid the circumstances which I can stop or maybe minimize the production of the ions are there. Okay. So once I am using this atomic absorption spectroscopy or emission spectroscopy or any X-ray methods, so I will use the atoms in the gas phase and then by using my qualitative and the quantitative analysis. But these ions are very useful when I am doing the analysis of the ICP-MS and even simple mass spectrometry also. See, one more thing, why this is basically there is a lot of questions generated in the people, and what is the difference between the ICP OES and ICP AES? See, when we talk about, because ICP AES generally we are using, I don't remember the exact year, but basically a using more, I think more, maybe before the 2004, 2004 only. Because at that time our emission spectroscopy or our detection ability, because now we are getting a detectors which are having a less than about say 4 picometers of the resolutions are there. Here we are not having. So nowadays, whatever the ICP is there, we can use both atom as well as the ions. So there are many ionic lines also there in case of emission spectroscopy which can be used. So that's why now the combined term as ICP OES. Okay. So, but in case of a ICP-MS or MS, I need only the ions for it because here the separation based on the M by E ratios are there. So, in case of a liquid sample, what is the liquid sample is there? So, you have a solid sample are there. So, you prepare a solution, you prepare a liquid out of it. And once you have a solution, then again in the solution you are having a compound. So, how to generate a atom from this compound? So, what are the various steps are involved in this? This involve the again ablation. Ablation nothing but say basically you have to generate aerosols. Aerosols meaning tiny droplets of the liquid. And once you have a tiny droplets of the liquid, you dissolve it. Desolvation means you have to evaporate the completely water molecule associated with that molecules. So that is called a desolvation. And once you have dissolved it, you vaporize it. So you bring your molecule in the gas phase. So again, then all the process will be the similar only. Once you are atom in the gas phase, you can get it. Then the second thing is that you can generate the atom in the gas phase itself by doing the sputtering actually. So there are many sputtering techniques are there by which you can bring the atom in the gas phase from the solid sample, and then again all the process will be the will be the same. So this is how various processes by which you can bring your compound molecules in the gas phase and from the gas phase in the atomic phase, and then you can proceed your analysis depending on whether you are carrying out the absorption spectroscopy, emission spectroscopy, or you are doing the mass spectrometry. This is generally a simple diagram for the atomic absorption spectroscopy. See, once you have an atom in the gas phase, basically, this is a very important step here. See, there is hollow cathode lamp. Basically, for example, if I am doing the analysis of a lead in my liquid samples, so then I will have a hollow cathode lamp of a lead only. So that means that it is absorbing a radiation so coming out from the lead only. So whatever the atoms of lead is there, they will absorb the radiation from the hollow cathode lamp, and then decrease this intensity of this radiation. I will measure it, and that will be corresponding to the my concentration as well as the this, qualitative and quantitative distribution. So generally we call this a line source. The line source may be a hollow cathode lamp, or it can be termed as a electrolytes discharge lamp. And nowadays, there is a, because as the technology is getting progress, so nowadays this hollow cathode lamp has been replaced by this continuum source. So that is called a xenon arc lamp, and the xenon arc lamp will give a basically from a on the wavelengths it can emit it from 200 to 800 nanometers, and then depending on the what you are analyzing, you can take the help of a monochromator, because all these instrumentation part will take care, and then you can get your analysis. See, atom cells. Atom cells means where you are doing the atomization. So, for example, in flame atomic absorption spectroscopy, flame. And now, if you are having graphite furnace, it means that atomization is being taking place in a graphite furnace. So, instead of flame, we are having a graphite furnace. And then, in case of some sample where there is a possibility of HYDRIDE generations are there, then we are using a quad cell. We will discuss all those things in the coming PowerPoint. And then detectors, we are having basically a photomultiplier. So this is the generally, the diagram which shows this construction of a line source, that is a hollow cathode lamp. So hollow cathode lamp basically a hollow cylinder. This is basically, this is basically a hollow cylinder, And here, the material, for example, if it is my lead HCl is there, so lead will be coated here. My element of interest will be coated here. And all those things will be either put as a helium or argon, and that too at a very low pressures. And how this work is that the lamp gas is under a near vacuum condition, and this electron flow ionize the gas, and the cation bombard the cathode to vaporize the metal. And the combination of the ion atom collision or electrons atom collisions and other process excite the electron inside the metal vapor atom, which emits the light, and that's how the particular wave will be generated and will be placed for the quantifications of the angular test. Then this is the basic construction of the xenon arc lamp, which is a continuous one. And nowadays the electroless discharge lamp is also coming into market, and it's having a similar to hollow cathode lamp in its use, and it produces spectral light by the RF excitation of a metal salt used for volatile or a non-conducting materials. So these are the various line sources are there. You having a hollow cathode lamp, you can have a xenon arc lamp, and then you can have a electroless. You can have a electroless charge lamps. And these are the various atom cells are there. So this is a flame basically. Here we are using the, whenever you are looking for a less volatile material, more volatile material, then we can use it at a lower temperature, so that here is clean flame. Here is clean flame, which is at a temperature about 23 to 100 degrees centigrade. And when you need you are dealing with a compound which needs a high temperature, in that case, we are using a mixture of a nitrous oxide and a acetylene flame to generate the temperature. Because the temperatures here, the acetylene flame cannot go beyond 2300 degrees centigrade. At that temperature, it's difficult to break the molecules and to bring into the atmosphere. Whereas in some cases, high temperature required, then we will go for 3000. This nitrous oxide acetylene flames are there. And basically, these are the burners made of tantalum, and these are the size of the flames are there. So the size of the flames are about 100 millimeter length in 0.3 millimeter wide in case of air acetylene, where the nitrous oxide is about the C is more concentrated, 50 mm length and 2.5 meter wide floats are there. So these are the reactions which are going in the flame, which producing a that heat. So the in the primary reaction zones, we are having both hydrogen, oxygen, and the hydroxide radicals are there. And this secondary zone, these the final products are there. And then we have a hydrogen, carbon monoxide, and a water vapors are there. Then we are having the secondary reaction zone that we are having a this carbon dioxide and water vapors are there. Whereas in case of the air acetylene flame, so this is the acetylene react with this nitrous oxide, and that's how we generate the temperatures. So basically, primary reaction zones. So we are having the blue flames are there, that we call blue flames are there. Then interconal regions are there, and this secondary diffusers are there. Then the second atom cell. This is we have discussed about the flame only. So these are the flames are there, and these are the reactions which gives that high energy. These are the reactions responsible for giving the temperature of 2300 degrees centigrade or 3200 degrees centigrade. So what is happening in the graphite furnace? The atom cell in the graphite furnace, that the carbothermic reduction is going on. That the metal oxide reacts with the carbon, and then now this reaction is going on. The advantage of this using, in which cases we use the flame and which cases we use this graphite furnace. See, whenever you are in this small volume of samples, see, for example, here for carrying out the analysis of the sample, we need at least 5 ml of the samples are there. But there are certain biological samples are there. Here you are having, microliters of the samples are there. Microliter, maximum 0.5 ml solutions are there. And in that 0.5 ml of the solution, you have to do, few elements are there. So in that case, it is always better to use the graphite furnace are there. And the quartz furnace, this is only basically there are certain elements. I'll show you what are the elements where we use this quartz furnace. And this quartz furnace probably for the generation of the hydride generation. So in I think we have already discussed this part. Basically, the flame atomic ionization may first part is nebulizations, followed by desolvations, and then the volatilizations. When the you have volatilizations, there are three types of particles that exist in the flame. That is atoms, ions, and the molecules. So this is now sequential flow diagram by which you can start with the solutions, and then you are ending with the say atoms or ions in the flame used for the characteristic as well for the characterization as well for the quantification of the elements. And this is the process which basically this particular power plant is just to show that in a few seconds, about say 40, I think the temperature, the whatever the liquid sample is there, so it will dry in 40 seconds, and then in another 80 seconds it will char, and then completely within about say 100 seconds. So all this atomization process takes just about 100 samples, and in this particular graph as shown is both standard as well as for the sample actually how this atomization is going on. So as I told you, these are the parts where we generate this hydride generator. So hydride generator, there are certain hydride forming elements are there. What are those elements are there? Arsenic, selenium, antimony, whisper, tellurium, tin, germanium, and lead. And that we can do the analysis at a very, very low level, that is part ppb level, that is part per billion. And then if you combine if you want to use mercury, then you can combine it with mercury concentration, and that can be done by using the cold vapor methods. Again, we can get detection limit of 1 ppb as routinely possible. Okay. And when you combine the mercury concentration, you use in conjunction with the hydride generator and add parts per billion. The key levels of the capability can be obtained when you hydrated this thing with the mercury concentrator, hydride generator. So this is basically that shown in the detectors. Detector is nothing but say photomultiplier tube. And photomultiplier tube, we got about the electron multiplication in the range of 10 to the power 6 to 7 now we can generate. So there are certain 12 diodes are there, and that gain is proportional up to the 0.7. The voltage about 0.7. Okay, and here n is the number of diodes, that is 12. And see, basically these are the various materials. See, as the technology is getting progress, first is coming the bialkali metals only. But nowadays this the diode which is prepared by the gallium arsenide are there. So there you can go up to the wavelength up to the 1000 nanometers. So this capability of the system will be enhanced tremendously if you are using the diode by using the your diode material and gallium arsenide are there. Okay, so these are basically how the quantification. Again, since it's an absorption spectroscopy, so it's follow the Beer-Lambert law. Okay, and then similarly, there are also these saturation comes whenever the high concentrations are there. So the plateaus are there. So generally, high concentrated samples has been diluted to get the accurate result, because once you are preparing a calibration curve, so and then if you are not getting your results as per the satisfaction, then you can look basically you can dilute your samples and get those things actually. And these are basically other regions, that is stay and ununiform distribution of atoms in the atom cells, and the non-chromaticity of light from the source. And this the analytical figure of magnets, the sensitivity, these are the various figure of magnets of the instrumentation, sensitivity, characteristic concentration, and then the correction limit itself. Okay. So this is how, as I told you, from the beginning, that none of the equipment, because the equipment will give a signal. You have to tell to that particular software that this signal is coming at what concentration. So that's why we have to do the calibration this thing. And in this particular case, basically, showing the analysis of the copper there. So basically, you are having a 0.05 milligrams of about say 50 ppm solutions is there. So out of this 50 ml solution, you will make a calibration curve by making it, 1 ml, taking the 1 ml of the stock solution and 2 ml, 3 ml, and then dilute it by in the volumetric flask. So that's how you can generate a calibration curve from the 1 ppm to 5 ppm. Okay. And once you have this calibration curve is there, then you can do the any unknown samples, and then whatever the wherever the observance is coming, that observance will correspond to that particular concentration. See, one thing which is very crucial in all this thing analysis. See, once you are carrying out any analysis, see how you make sure, because this is having a good combination of both optics as well as the electronics. Another. So in all those things, there are certain thumb rules are there. See, by which you will know whether your optics is working properly or not. So in this particular flame atomic absorption spectroscopy, we have prepared a solution of this 5 ppm solution of the copper standard is there. And if you are getting a absorbance about say 0.7, then it means that your optics are more or less working satisfactory. Basically, it's a thumb rule when we are using the atomic absorption spectroscopy. Now, as other technique, all the techniques having some kind of other kind of backgrounds are there, and to get in a correct results, so one has to do the background corrections are there. See, these backgrounds are coming. What is happening in this background? See, in absorption spectroscopy, what you are measuring, you are measuring the intensity absorbed by your atoms as well. So, what are those things in the process are there? Because when you are using the flame, in case of flame, there are so many unburned molecules are there. So those unburned molecules also will get absorb those light. And then finally, because you are measuring the decrease in intensity of this HCl further. So you're ending up with the higher values. So these are the things has to be corrected actually. Those background has to be corrected. So these corrections basically once you have make a calibration curve. See, if you are not getting a calibration curve, proper calibration curve means what? See, if you are not getting a R-square value of the order of 0.99 as a better, then it means that there are certain kind of background, the system need a background corrections are there. So what are those background corrections? So either they will continue those corrections. Then second one is the ZEEMAN effects, and then third one is the source self-reversal, that Smith-Heffey corrections are there. Generally, actually Smith-Heffey correction we does not carried out, or you could say unpreferred corrections are there because they're very rarely required. And since because of this, it has to one measurement has to be done in a low current and a high current. And when you do when you give a high current to your HCl hollow cathode lamp, it means you are decreasing the expected life of that particular HCl. So that's why it will be avoided. Otherwise, this continuum and source correction, for which we are using the deuterium lamp, and the other one is the ZEEMAN, where we are applying a magnetic field around your atomic cell. So this is that generally how we avoid this how we carry out this continuous source corrections by using the deuterium lamp. And then this is what is happening, the continuous source correction, which is showing carrying up to the 450 nanometer. And all those absorbance basically coming out from the molecules, unbound molecules, which is carried from the flame. And basically this is how we carried out these continuous source corrections. and the light from these hollow cathode lamp is absorbed by both sample and the background, whereas the light from the deuterium lamp is absorbed entirely by the background only. So once you minus this from this, you will get the correct decrease in intensity, and so that you can do this continuum source corrections by using the deuterium lamp. Other way is that the ZEEMAN effect. In the ZEEMAN effect, what is happening? An alternating magnetic field is applied at the atomizer. Atomizer here basically is a graphite furnace, and that is split the absorption line into the three components. That is pi component, which remain the same position as the original absorption line is there, and the two sigma components which are moved to higher and a lower levels actually wavelengths respectively. And the total absorbance is measured without magnetic field and background absorption with the magnetic field on. Now, what is happening is the pi component has to be removed in this case. For example, using a polarizer, and the sigma component do not overlap with the emission profile of the lamp, so that only the background absorption is measured at this time. And what is the advantage of this technique? That the total and background absorptions are measured with the same emission profile of the same lamp, so that any kind of background, including background with fine structure, can be corrected accurately, unless the molecule responsible for the background is affected by the magnetic field, and using a chopper of a polarizer, reduce the signal to noise. And while the disadvantage are the increased complexity of the spectrometer and power supply. See, one more thing I will tell you. See, these are all for your understanding only. Actually, when the software is coming, whatever the instrument is being supplied to you, it's coming all the software is having all these are inbuilt procedures are there. See whether you want to do the continuous background corrections by using the deuterium lamp, or you want to apply the alternate magnetic field for carrying out the ZEEMAN corrections. And as I told you, this Smith effect correction, which is not very popular one because it will increase in the current, because you have to carry out the measurement at a higher current, and that's how it will decrease the expected life of your the hollow cathode lamps. But generally, this also comes in the feature of this system, and here you can see where this is the absorbed by the sample, which is not completely eliminated, but the background are absorbed the same portion of the light. And then here the absorbed by the sample and the background. And then finally what you get the atomic absorption. So this is how we can carry out the Smith effect correction. Then there are many spectral interference are there. Spectral interference means the elements keeps having many absorbance at many lines are there and wavelengths are there. For example, in case of this vanadium and aluminum is there, and you want to do the analysis of the aluminum only. So since this line of the vanadium and aluminum are so close, the one is at the 30282.11 angstrom, and other one is 3082.15. Then what we can do is better, always to choose a line which is far away from those things. So it's here, in case of if you are carrying out any analysis which any solution which contain both vanadium and aluminum, so choose an aluminum line which is free from this spectral interference are there. So then we choose the line of it 3092.7 angstrom zone. So this is how one can avoid the spectral interference. Background absorptions, I already told you that one can use this continuous source that is deuterium lamp, and this it will be possible up to 350 nanometer. These corrections carried out up to 350 nanometer, and a deuterium source lamp is used for the background correction, which comes already fitted into the atomic absorption. As I told you, these are the facility which is already inbuilt in the instrumentation. Only if you are not getting a proper calibration curve, you can ask him to carry out the whether ZEEMAN corrections or a event corrections or a this continuous source correction that is the deuterium lamp. So that's how you can avoid these background corrections. And then there are certain interference because that will count as a chemical interference. For example, here we want to do the analysis of the calcium in the presence of a sulfate and a phosphate. So what is happened, this because both of this the stability constant of this calcium sulfate and calcium phosphate is very high. So it's very difficult to, and you know that you need a calcium in the calcium atom. Actually, you have to break these molecules. So what you have to do? You have to add in something, some other reagent into this thing, which having a better stability constant. Okay. So for example, in this case, we are adding as a releasing agent. So that's why lanthanum and strontium are a good releasing agent for calcium in the presence of a sulfate of a phosphate, because the lanthanum phosphate strontium sulfate stability is much better than compared to calcium sulfate and the calcium phosphates. Similarly, lanthanum and strontium are a good releasing agent for magnesium in presence of a aluminum are there. Or what are the other things? Because you have to break the molecule. You can use the water flame actually for breaking these molecules. But generally, what we prefer to add the releasing agents are there. And there are certain agents, they are called as a protective agents are there. For example, ETT and 8-hydroxychloroquine are termed as a protective agent. Why they called as a protective agent? Because they can complex calcium in presence of a sulfate and phosphate and aluminum. And then it's very easy to break this calcium, EDT or calcium actually compared to sulfate and phosphate. So you can add any of this. There are three ways. You can use the water flame, you can add the releasing agent, or you can use the protective agent. Then the next one is the ionization interference effect. This is basically ionization interference effect means that there are antimatter which can easily ionize it. So there is a lot of electrons are available into the flames are there. So how to overcome those things, these problems? So you can use the low temperature flame, or one can use the ionization buffer, also known as ionization suppressors or ionization suppressant, which prevent the ionization. And ionization buffer is the salt of an alkali metal which ionize to give a mass of electron that shift the ionization equivalent of an electron to form atoms. And generally, in all these cases, we prefer to add a 0.1% of a potassium chloride. This solution added both blank and standard as well as. See, now here is very important, as I told you, whether the process blend and the standard blend. So there also you have to do the addition. If you remember in my vocabulary, terminology and vocabulary, I told you process blend and the sample blend. So this is how these are very important term. So you have to add this 0.1% of potassium chloride to blend, standard as well as the sample. So what will happen? Because the potassium will be easily ionized, and this gives an increased concentration of electron in the flame and drive back the ionic form to the downstream where they absorb at a right wavelength. So this how by addition of this 0.1% of potassium chloride, this ionization interference effect can be controlled. So this is just sum up of the atomic absorption spectroscopy. So in case of atomic absorption spectroscopy, either using the atom cell of a, there are three atom cells we have discussed. One is the flame, other one is the graphite furnace, and third one is the hot cell, where the HYDRIDE generators are there. So you have a simple sample is there, and then this sample you have the atom formations are there. And once the atom formation is there, this atom will get excited by using the hollow cathode lamp. So in that process, while doing the excitation, that particular wavelength will be absorbed from the HCl. And if we are using a continuum source, we use the monochromators so that particular wavelength only will go. And this absorption, when taking the atom from the electron from the ground state to the excited state, the decrease in the intensity of this hollow cathode lamp will be measured, and then decrease has been recorded at the detectors, and then how we quantification actually. First the calibration curve, and then the unknown sample. This is how we are, handling up the atomic absorption spectroscopy. We are coming to this emission spectroscopy. See, atomic emission spectroscopy, as I told you, AES or OES. Now I think you have to understand the difference between the AES. AES, we are only discussing about the atom. Okay, as you say, the A means atoms only. And optical emission spectroscopy, we can take the emission lines from, not only from the atom, but we can take from the ions also. So this is used for both quantity measurement of the optical emission from the excited atom and to determine the analyte concentration. Analyte atom in the solutions are aspirated into the excitation region where they are desolvated, vaporized, atomized by using plasma. So this is how this desolvation, vaporization, and then atomization, and then ionization, and then we do the detections. So this is just simple, what are the processes going on? The plasma is there, and from the polar chronometer, and then goes to the detectors. See, you have seen in the case of atomic absorption spectroscopy, we are having a maximum temperature about, say, only about 300 degree centigrade. So, but here in case of this ICP-OS, that is where we are plasma. So here we can reach up to the temperature about the 5,000, because basically we can go to temperature about 10,000 Kelvin. But most of the measurement which we carried out, the analytical the temperature range of a 5,000 to 6,500 degrees centigrade only. So this is, you can see that in case of a low temperature, there is only few atoms there. When we increase the temperature, the number of atoms with the emission lines are increasing, and when we reach the about 5,000 Kelvin, the number of atoms will further increase. So there are basically 6 basic components of an ICP. That is sample interaction, energy source, then spectrometer, that can be lens, consists of a lens, mirrors, and a grating, and detectors. Detectors can be, can be photomolecular tube, or it can be charge coupled detector, that's CCD, or it can be CID. Then serving associated electronics, and then computer and the software. So these are the 6 major part of the systems are there. And emission source basically of the flame, arc, spark, direct current plasmas are there, then inductively coupled plasmas. So this is basically a 3 plasma torch, basically 3 concentrated rings are there. In one of the center ring, the sample carrier gas is flow, and then the auxiliary gas and the coolant gas. So before going further, I'll let me tell you. See, basically in most of the cases, earlier we are using argon and nitrogen. So where the nitrogen is used only for the coolant gas only, and the auxiliary and the sample carrier gas we are using argon. And why we use argon, that also we will come to know. See, here we are nowadays replacing all this with this one single gas. Just for the, of course, it becomes a little bit expensive, but for the ease of operation, it becomes easier, because now I'm using as a simple only argon as a gas for coolant auxiliary and the sample carrier. Okay. Then what are the plasma advantages are there? For high temperature, allow for a full dissociation of the sample compound. And then argon is a non-reactive with samples, and the linearity analysis of sample from ppm to ppm range can be done in a one go. And matrix tolerance is very high. It's a robust, flexible design, and nowadays coming with PO and axial view actually means axial and a radial view, both are there. PO view, one is vertical, other one is horizontal. So that also point. How various temperatures beyond in the plasma are there, and as it told you, see why we use argon, because argon optically transparent both in the UV visible region. So that's why there is no interference, and its first ionization energy itself is very high. that is 15.75 dB, and it's having a very low thermal conductivity. And this is how this this generation of the process, which is the pairing ionization and the excitation, that is argon ions will react with X, and then it will give you argon atom plus X plus minus and then electrons, and spontaneous emission from the ionic levels, and then recombination and spontaneous emission from the atomic level. See this, I think whenever you have a free time, you can read it how this plasma get generated. See this, in this plasma get generated, basically all this instrument which is coming, the plasma is coming at two different frequencies. One is coming at 27 megahertz, other is coming about 47 megahertz. I think these are the two most desirable frequencies which available there. And these generations of this plasma, because basically once the electron get initiated, because there is one Tesla coil is there, so once the argon get flow, first liberation of the electron will be done, and then those things will be get moving in the spherical tube that argon gas will move in a electric and a magnetic field. And with that frequency, so 27 megahertz. I think what we are having 27 megahertz. So at that high frequency, there's a lot of friction will get generated, and because of that collisions, we get a very high temperature. See, all these things have been very written nicely. It was not possible that otherwise it take about 10 to 15 minutes to explain how the plasma get generated in the system. And the maximum temperature we got around 10,000 Kelvin, but basically we concentrate in the analytical zone of about 6,000, 5,000 to 6,000 Kelvin. And this is a simple block diagram of the ICP OES. And you can see here, actually, in all the cases, we are putting the coolant auxiliary, and this thing we are getting argon only. And this part of the nebulization and the spray chamber, I will show you the details to this thing. And then we'll discuss about the detector, both in case of a simultaneous detection as well as in the case of a sequential detectors. So in case of sequential, we are having these PMTs are there, and then in case of the charge simultaneous detector, we are having the CCD. Actually, nowadays CCD has been replaced with this CID also. Yeah, so मालूम पड़ रहा है आगे जा रहा है. Yes. Okay. So this is the basically okay. Now before going further, you can still if any queries are there, boss. Any one of you have any queries, please ask me. See, I think we have finished almost this absorption spectroscopy, and as well as this some part of this emission also. If you have anything. How many people? I think कितने लोग? दो ही लोग हैं ना? Sridevi, are you listening me? Sridevi, no? Hello? तीन लोग हैं. याद है? हाँ? See, anyone, if you want to ask any question also, you can unmute your mic and then ask your queries. Because already 5. Okay, so basically now we'll go one by one. You will see that how these pericyclic pumps looks like, nebulizers, and then the spray chamber. So these are the pericyclic pumps are there. The pericyclic pump is that you are putting putting the liquid into the nebulizer in a controlled manner, and nebulizer is the process by which you are breaking the liquid into the aerosols, and this is the spray chamber. Basically, the spray chamber from where the your this aerosols which is coming out the liquid will go into the plasma, and whatever the major large droplets are there, they will be drained back into the drain system. Question? Huh? Yeah, कुछ तो question है. So there is some interference in case of AS. Yes, that's what I told you. No? There are many interference in case of AS. There may be a this interference may be of the chemical interference. This can be ionization interference, or the background interference are there. So it means that, and how you come to know these interference? See, once you are not getting a good calibration curve, okay. So that's how you will come to know that the systems are. You have to do those corrections are there, or sometimes. See, sometimes basically you are looking for some concentration. For example, if you are measuring the concentration of the calcium, and you know that my calcium concentration will be in the range of 5 ppm, but you are getting only the 3 ppm. So then you will look whether there is some sulfate or phosphate ions are there or not. See, until unless you have to do those various pros and cons of your with your sample, you have to do hidden trial in that method for looking the probable interference. If you know about the metric, then there is no issue. That if you know that you have to analyze the calcium, presence of sulfate and phosphate, so then definitely you will, in the beginning itself you put the lanthanum or the strontium, so that will be taken care. And the second part of the Chakravarti is that which metals are difficult to detect or interpret, showing wrong results. Kindly let us know. See, basically, more or less, it's a fixed. For example, if I'm using the rare earths, so rare earths I will never use by using the AS or FAS. Okay, because I know that it's very difficult to break this compound of the rare earths at a low temperature regions. Understand? So in that case, I myself will go for the ICP-OES. And ICP-OES also, there are certain system which having a good regulations, because there may be many interferences are there. So it's not very easy to tell me that which metals are difficult to detect or interpret showing wrong results. So unless you are dealing with the samples, what is the sample matrix is there, and what are the scenarios are there, you have to yourself look for those things. And that's why here comes the importance of the CRM or SRM actually. Once you are having a CRM or SRM matrix matching, then this kind of a problem will not be there actually. Then you are aware that I am going to face this problem and how to overcome this. So there is not a very unique answer that which metals are difficult to detect or interpret. Generally, the if you characteristics the metal, mercury, arsenic, because they are the volatile elements are there. So one has to take the proper care actually. So if arsenic has to be done, it is roughly done by using the HYDRIDE generation sound. If you are using the AS and flame atomic absorption spectroscopy and using the arsenic, then it's a high concentration is okay. For example, I am looking at 10 ppm of the sample of arsenic, then you can do by using the flame. But I am looking at low concentration, then definitely I have to go for the HYDRIDE generations. So that's how we have to do it. Okay. Now this was ये बराबर दोनों काम किया अभी ठीक है. So this is that block diagram of this sequential spectrometer. Sequential means each element will be analyzed by one. Okay. And for this, we are using the, in case of this thing, detector is the photomultiplier tube is there. So if I have to do the analysis of the of the sodium is there, so I will do the sodium. If I do the lead, I will use for the lead. This thing. So sequentially, I will do the analysis. It's basically is a more sensitive one, but say time consuming. Whereas in case of a simultaneous spectrometer, see, I am getting this the wavelength of from all the elements at a time, and then by using the which element I want to analyze, then one by one I can select it and then do this. See, it's basically it will scan all the elements and it will come at a time to the detectors. And then the analyst will look for one by one that because if I have to analyze the sixth element, okay, all the six element comes at a time only to the detectors. Then one by one I can go and then do the analysis. Say less time consuming, and of course there is a we have loss on a in terms of sensitivity. There is some small losses are there, and this is basically one from the primary slits. All the things will come at the same time to the detectors. As I told you, this is basically possibilities are there. You can have a radial views and the axial views. See, radial view means it's a robust and a fewer interference because it's take a smaller path actually. Smaller path of the light is there. Okay, it's only smaller part of the light is there. Then we have axial view, it's having best sensitivity, but we are losing on the in terms of the detection difficulty. And then why? Because why axial advantage is there? Because much more light are available, and this give you the give us the opportunity to achieve lower detection limit than radial view. But unfortunately, more matrix interference and slightly reduced dynamic range are there. Dynamic range means lowest to the maximum, so that will the dynamic range also will be get reduced are there. But nowadays, systems are coming where it is possible to view both the radial and the axial views are there, and the provision has been provided that you can do the analysis either using the radial view or the axial view. That we call as dual view. This is the concentrating numbers. So basically, three concentrated rings are there. And sample preparation part, we have already seen it in the sample preparations. So there are the same things are there. And the derivation, how we carry out the samples, derivation. And this also we had discussed the various kind of fluxes, but I told you, because maximum salt tolerance is about say maximum is about 5% only. So the salt concentration should be less than 5%. So, but in case of a fusion, we are getting high salt content, so more dilutions are there. Dilution is more there, and because of the dilution, the chances are getting that you are getting a more at the surface in your final calculations. Now coming to the last part of the today lecture, that is mass spectrometry. See, mass spectrometry is an analytical spectrometry methods. Tool primarily concerned with the separation of a molecular and a species according to their masses, and what information can be determined from this mass spectrometry molecular weight, molecular formula, then structure, because of the we can have fingerprints of various structures, so we can elucidate the structure of the compound, then the isotopic incorporation or the distribution, and of course in case of tandem mass accelerator, that is a combination of two mass spectrometers, so we can do the various kind of protein sequencings. So these are the various part of the mass spectrometers. It contains an ion source, a mass analyzer, and then the detectors are there. And the function of the ion source is to produce ions from the sample. The function of the mass analyzer is to separate ions from the with different mass to charge ratio, because here the separation is based on the M/E, that is mass to charge ratio, and the number of different ions are detected by the detector, and finally the mass spectrum and generated with the data analysis units are there. So sample ions, ion source are there. So because of that, that we'll see that what are the different kind of ion source are there, what are the different type of mass analyzers there, and then what are the different kind of detectors are there. So sample is first vaporized before passing through an ion chamber. They bombard with a stream of high energy electrons, and they result in the formation of a molecular ion as well as the number of fragments. And these ions are then fed into electric field where they are accelerated. Basically, these we call say optical lenses and pass through a narrow slit, producing a narrow beam of positive ions. Okay, so this is how this ionization and fragmentations, and then this beam is then subjected to magnetic field, causing the ions to be reflected at a particular distance, depending on their mass to charge ratios. And these ions reflected are detected. The reflected ions are detected by a particular instrument, which are then sent message to recorder, and then how we generate the mass spectrum. Now, this is basically ethanols are there. So, various fragmentation of ethanols, and then how we detect it in various fragments when the amyloid ratios are there. So, this is general block diagrams are there. So, this is okay. Ion source are there, electron beam, then insulator ion beam, and then how it goes to the magnet where we are doing this ions that are applied are much bent, they are reflected as was there, M by E ratios are by E ratio. And then it's coming back to the detectors, and from the detectors it will go to the order where we get the spectrum. See here, one more important thing is the whole your mass spectrometers, it has to be in a high vacuum. Why we need it in a high vacuum? Because we want this mean free path should be very high, and because during this flight of this system, because when they are reflected here, they should not interact with the atmosphere, because otherwise they will interact with the different particles of the atmosphere and get lost. So there is nothing will come into the detector. So that's why all these mass spectrometers are kept in high vacuum. So there are various types of ionization methods are there. That is electron ionization, chemical ionizations, then desorption ionization, fast atom bombardments are there, then electron spray ionizations, and atmospheric pressures chemical ionizations, and MALDI, which is very important, that is matrix assisted laser desorption ionizations. So these are the various 7 ways by which you can bring the ionizations of ionization, and then there are the various mass analyzers there, that is the magnetic magnetic sector analyzer, that is called MSA. And what are the advantages in this? High resolution, exact mass, and then the original MBI. Then quadrupole mass spectrometer, that is called say advantage is that it's will go up to the as low as 1 atomic mass unit. It's very fast, and then compared to the other one, say cheaper actually. Then becomes the time of flight, that the no upper and by jet limits, and then the throughput when you have a large number of samples is always preferred to have a time of flight mass spectrometer. Then we having untitled mass analyzer, that is a good resolution, and all-in-one mass analyzers. Then cyclotron resonance, that is FTICR, that is highest resolution, exact mass, but it's still very costly one. And my detectors, basically in the early stage is only photographic films, but today detectors will produce electronic signals up to second degree electronic emission when struck by an ions, and then timing mechanism integrate this signal with the scanning voltage to allow the instrument to report which MYZ has struck the detectors. And this is a constant and a regular, but it is a constant and a regular calibration. Then detectors, these Faraday cups, electron multipliers, and micro channel plates, and then inductions are there. And the uses of these different detectors in isotope mass ratio, we are using Faraday cup. Then it's basically very common the electron multiplier detectors. And in case of a higher end instrument, which is very sensitive and is hostile one, then but it's a higher end instrumentation. We use the micro channel plates, and induction uses the FTICR, which is it's still very costly and very used in this used for some special regions are there. Okay, and basically what this information what we get it, see for example chlorine having a two isotope ratios are there, that is 35 and the 37 elements are there. So what is the ratio when we do this analysis of it? Then what we basically ethyl chlorides are there. So once we do the analysis, we come to know that's only the one chlorine, single chlorine atoms are there, and the ratio of M to M plus 2, which is approximately 3:1, given a presence of a single chlorine to the compounds are there. Similarly, we are having this bromine, that is propyl bromides are there. So propyl bromide also, because the ratio is 79 to the bromine which having two isotopes, the 79 and 81. The ratio of 1:1 indicates only one single bromine compounds are there. So that's how we come to know such propyl bromides are there. So that's how this mass spectrometric used for illustration of the structures. Okay, and the other applications of the mass spectrometry is identifying and quantifying the pesticide in the water samples, identifying steroid in the athletes, and doing the metals at a ppb, that is parts per kilogram. It's such a low level in the water samples. And basically, when we are looking at various kind of drinking water, as per the WHO norms, one has to use this mass spectrometers, and then can use for the carbon 14 dating, to know the age of the various whether it's geological structures or any others, matrix in the nature, which having a contact with the nature, the natural carbon dioxide, so we can use the carbon 14 for determining its age. Then determining the mass of a 28 silicon atom with an accuracy of 70 ppt, and studying the effect of a molecular collision angle on the reaction mechanism. So this is basically, a comparative decision-making matrix, which instrument has to be used actually. Okay, so when you are using a single element, it's better to use the FAS. When you are using few FAS, so these are what level actually may the elements, levels, and samples throughput. Okay, and then the quantity also. So all those four things on the basis of this 1, 2, 3, 4, 5. Actually, with this four thing, one can decide which instrument is better for its analysis. Of course, ICP-MS we are not covered it, so that we will see it later on stages when we are discussing this hyphenated techniques. So these are the things which general cable on the basis which technique has to be used for which sample. Then there are the interferences, various interferences associated. In case of flame AS, we are having ionization group or releasing agent, or we can use the low temperature flame or high temperature flame, that is high temperature nitrous oxide acetylene, and low temperature means clean oxygen flame. Then if you are not properly the proper beer lambda, you can dilute your sample. Then matrix matching methods or method of addition actually. You can look this interface by the either using the matrix matching or by the method of addition. That is, you spike your analyte into your sample and then see whether your signal is getting enhanced or decreased because of the matrix interferences are there. Then graphite furnace, this is having physical and chemical and molecular absorption spectra. So this is how we can compensate it. Spectral standard temperature platform, furnace conditions, standard additions, ZEEMAN or the continuous source background corrections, or ZEEMAN background corrections. So this is how we can compensate all those molecular absorptions or spectral interferences, or maybe due to the physical or the chemical form of the particular samples are there. So ICP-MS, spectral and matrix for background corrections, or the use of alternate analytical lines. Matrix is internal standardization. Internal standardization is the method, standard additions are one of the best methods to do the matrix interferences. ICP-MS we will discuss later on. Then AS, single element, ppm to pp range, C, small dynamic range, graphite furnace, atomic absorption, about 100 times more sensitive compared to flame atomic absorption, but also more challenging. Then ICPO is a multi-element and the range is the PP range, limited spectral interference, good stability and low matrix interferences. Of course, when we discuss about this MS, ICP, MS, multi-element possible, even in MS also, to reach PPT or PPT or even PPT levels also, subcontrol levels, and most complex but most expensive, low detection limit. Isotope analysis are possible by using the MS. So that's I finish with my today lectures on the spectroscopies now, and request you if you having any questions now or even afterward also. My email ID is there, and as I told you from time to time, see, because of the constraint of the number of lecture to be accommodated for the one course, I've been asked to give the all the covering the all the topics of the analytical chemistry, and which is not possible actually. See, one person cannot be expert of all the fields, but I try my best and to satisfy if your queries, if your any queries there, I try to answer myself. If not possible, I will take the help of my colleague to respond to your queries. But I request all of you, because some of you may be going to opt for the exam also. So please come forward. Don't keep any query. Whatever it looks to be very elementary or big, because I know it's, you are belonging for the multidisciplinary field. So please come forward to ask any queries if you are having. Yeah, yes, sir. Actually, I'm trying to give a physical lecture rather than all of you can unmute your mic actually, me. Okay? Any queries there, Gunjan, Chakravarti?
No, sir, I don't have any doubts.
You are a chemist or any other discipline, belongs to other discipline?
Sir, I'm doing my master's in chemistry right now.
Okay, from where?
Sir, from Shivnada University, Delhi.
From?
From Shivnada University in Delhi.
In Delhi?
Yes, sir.
Delhi, I'm from Delhi only, but because I never heard such. Okay, Abhi, it's open, right? How old is this university?
So it's only around 9 to 10 years old.
Oh, 9 to 10 years old. Because I was out from Delhi from 1988. I had done my BSc from Mansraj College in 1986, and then moved to IIT Delhi for MSc Chemistry.
Okay.
Okay. So, but Navita, you may be having many queries actually, because being a chemist, any other thing coming in your mind? Because you had asked me just a general question, because there is no state questions to answer that which matters, because it depends on the matrix. For example, if you are doing the arsenic analysis in the water sample, it's very easy. But if you similarly do the arsenic in the soil sample, then it's become a difficult actually. Then at what concentration? So those are the things, are the deciding factors which technique has to be used and what kind of precautions to be taken out to be taken during the analysis. Okay. Shall we move? Okay, boss. Bye then, and we'll see you on the for the next lecture.
Thank you, sir.